objects have kinetic energy, and objects that are above the ground, or above wherever we happen to call zero, potential energy. And the combination of those two things we call the mechanical energy of the object. And as the object moves around, think of a ball going through the air, the energy can swap back and forth between kinetic and potential. As it goes up, the kinetic turns into potential, and as it comes back down, the potential turns back into kinetic. But the total amount of energy will stay the same because energy is conserved. It doesn't just disappear. If you are losing potential, that has to go somewhere, and so that turns into kinetic. If there is no other outside force that is either giving more energy to the object or taking it away, then the mechanical energy will stay the same. And this is a very useful way to solve certain types of motion problems. Because if the mechanical energy stays the same, if there's no work being done on the object other than by gravity, which is built in, if the mechanical energy stays the same, that means the total of kinetic and potential on both sides stay the same. Which means if you add up the potential and kinetic at the end, it equals the potential and kinetic at the beginning. Now look at this. I mean, it's a long equation, but look what's in there. Height, which we can measure. More importantly, look, there's VI and VF, which means you can use energy to calculate the velocity at the beginning and end, just like in a motion problem that we did with dynamics and kinematics. The nice thing about doing it this way, rather than Newton's laws, is all these guys are scalars. These are not vectors. You don't have to do any components. You don't break everything into x's and y's. You don't solve this side, solve this side, put them back together. None of that. It's just a scalar. It's just a number. They just add like 5 plus 2 is 7. It's beautiful. And so if you have a problem where all you're looking for is VI and VF, or VF, then using energy is 5 times easier than using forces and all that stuff. Now you will notice, however, there is no delta x in there. There is no time in there. There is no acceleration in there. If you're trying to find those things, then energy doesn't help you all that much. But if all you're looking for is velocities, then this is the way to go. It's a lot easier than doing forces and vectors and Newton's laws and things. So as an example, let's just say we're going to drop an object, drop a stone off of a bridge, okay? And I want to know how fast it's going when it reaches the ground. Now this is actually one-dimensional. And we could have solved this problem way back in Unit 2 when we talked about one-dimensional motion and free fall. And that wasn't too hard. But I want to show you how to do it using energy. Because if you understand energy in one dimension, you also understand it for 2D, since energy doesn't have a direction. So, stone dropped from a height of 12 meters. How fast is it going right before it hits the ground? I'll always have some smart students say, well, when it hits the ground, it's going 0. Yes. Fine. Right before it hits, how fast is it going? If you're laying on the ground and you see the stone coming towards you and like, oh my gosh, how fast is it going to hit me? So well, after it hits you at 0, it'll be like, well, thanks for that information. I really would like to know, as it's hitting me, how fast is it going? Okay, stone at the beginning, stone at the end. Right before it hits, it's moving. Okay. Up here, it's got some mechanical energy at the start, ME initial. Right before it lands, it has some mechanical energy at the end. Ignoring any effects of air resistance, those two are going to be equal to each other. MEF will equal to MEI. And what we're trying to solve for is VF. Okay? Well, that goes into kinetic energy. Let's put this whole list of stuff on there and just learn how to use it. A lot of the things will cancel out. That the mechanical energy at the end is the kinetic plus the potential. At the beginning is the starting kinetic plus the starting potential. Yikes, lots of little symbols. Yeah, but look, it's going to simplify really quickly. First of all, at the beginning, if you dropped it, how fast was it moving? When you dropped it, right when you were letting go, it wasn't moving at all. VI is 0 when you drop it, which means this whole term goes away. There was no kinetic energy right before you let it go. When it reaches the ground, it's at 0 meters, a height of 0 meters, which means at the end it has no potential energy. Here it's all potential. Down here it's all kinetic. So the height at the end, I left off my F, really need the subscripts. The height at the end was 0, so that kills all of that term. At the end it's all kinetic, at the beginning it's all potential. So let's just rewrite this so it's not so messy. 1/2 mv final squared is mgh initial. Now there's one more thing we can do. Both sides have an m, and it's exactly the same m, right? It's the same object. Let me go back to the question at hand. Notice, I didn't tell you the mass of the stone. You know why? Because you don't need to know it. It doesn't matter. You got an m on both sides. You divide both sides by m, and the m's cancel out. Not the whole term, just the m. We divided both sides by m. And so now we have 1/2 vf squared is gh, which tells you that all objects will fall at the same speed. It doesn't matter how big they are. If you drop a big mass and a little mass, they will fall, it's going to make a noise, they'll fall at the same rate, which they do. Knocked all my stuff on the floor too. Okay, so to find VF, we're almost done. You just multiply by 2, and then that's VF squared. You take the square root. So VF is square root of 2GH. Now, I'll quite often have students say, well, should I write this down on my note card or on my little list of notes? No, because this is only true for a certain problem, for starting at rest and falling all the way to the ground. It's not true for all problems. What's true for all problems is this, okay, that the total energy is the same. So always start with that, okay. Oh, and I have lost my problem. There we go. So we're almost done. You just plug in the numbers, and we'll have its velocity at the end, square root of 2GH. Square root of 2 times 9.80 times the height, which was 12 meters. So it should be going fairly fast. Square root of 2 times 9.8 times 12 is 15.3 meters per second. Over 30 miles an hour, about 34 miles an hour from dropping 12 meters in the high. Not too bad. Okay, now let's make it a little harder. That was 1D. You're like, this isn't really that much easier than doing it like we did one-dimensional motion. My free fall problem would have been about as many steps. Oh, you haven't convinced me yet that energy is any easier than what we've done before. Now I will. Okay, we're going to shoot a cannonball from the top of a hill. It's going to come back down and land. This is projectile motion. Remember how joyously fun those were. You had to break all the accelerations and the velocities into x and y components. So all the x side, so all the y side, combine them. Took a lot of steps. Let me show you the same problem using energy. It will take you no more steps than this problem did. You'll say, I am sad that I had to do all that work back in the projectile motion section. Well, yeah, but again, you can find velocities from energy. You can't find how far away it landed. There are still times when you need to do it the long, hard way. Okay, so cannon's on the top of a hill. There's the plane. The cannonball is shot. You don't tell me what direction. That's true. You know why? Because energy is not a vector. It doesn't matter what direction. Some direction. Goes up, comes back down, lands. And I want to know how fast is it going right before it hits the plane. Well, it has some mechanical energy to start with. It's above, where should we call zero height, the lowest point in the problem. So when it lands down there is 0. So up here it's got some potential. mgh. It's got some kinetic because it's moving. And then down here when it lands, there's the final mechanical energy. And that's all going to be kinetic because it's reached zero. Like, oh my gosh, this is hard. There's all these steps. No, look. Watch this. The energy at the end is the energy at the start, ignoring any air resistance on the cannonball. At the end, it could have both kinds, potential plus kinetic. At the beginning, it actually does have both kinds, potential and kinetic. Okay, let me just write this down. Now, is anything zero? Yes, at the end, we're at no height, right? So there is no potential at the end. That goes away. And what else can we do? Every term has an m in it. So we can divide all the terms by m, and the m's go away. Now it's getting messy, so let me rewrite it. 1/2 Vf squared is 1/2 Vi squared plus Gh. And we're solving for Vf. If I multiply by 2 to get rid of that half, take a square root, we're done. 4 lines of work to solve a projectile motion problem using energy. If you don't remember how long that took, go back and try one, back from Unit 3. Okay, so multiply by 2, and then take the square root, Vf, square root of Vi squared plus 2Gh. Wow, that was quick. Now we just put in the numbers. Vi was 48.7 squared plus 2 times G times the height was 37.8. Get your calculator. Square root 48.7 squared plus 2 times 9.8 times 37.8. Right? Yep. Close. 55.8 meters per second. Now notice this doesn't tell me what direction it's moving. It just tells me how fast. But if that's all you want to know, if you're trying to shoot this cannon to knock down that fort, and all it really matters is how quickly it's moving when it hits, then you're done in about 4 lines of work. So, moral of this, if you can solve a problem using energy instead of using forces, by all means do so. It's a lot quicker because they're all scalars. Energy is your friend, and we will practice with him a little bit more.